Hey guys, welcome back to my channel. In this video, we're going to discuss how to efficiently virtualize the CPU with control and achieving maximum performance. The basic idea is simple. Run one process for a little while, then run another one and so forth. By the concept of time sharing the CPU in this manner, virtualization is achieved. But there are two challenges over here. The first is performance. How can we implement virtualization without adding excessive overhead to the system? The second is control. How can we run the processes efficiently while retaining control over the CPU? The operating system needs to be run on the CPU as well. If a given process runs forever, then the control will not be given back to the OS. The OS, which controls important instructions and is also in charge of the resources, will never get the control of the processor if a particular process hogs the CPU forever. So, obtaining high performance while maintaining control is one of the challenges in building an operating system. The basic technique to overcome this challenge is limited direct execution. Okay, direct execution basically means you create a process, you allocate the memory for the program, you load the program into the memory, you call the main, then the control is given to the process or the program. It will run the main, it will execute return from the main, and then the control is going back to the operating system once the process is finished running, and you free the process and remove the process from the list. Right? Simple to understand, it's easy. Okay, but over here there are two things to consider, the two problems over here. One is, if there is just one particular memory space which you are running on, the process can easily perform any restricted operations. Right, it can overwrite any file, it can request for an input output to a disk, it can gain access to more system resources such as CPU or memory. So to solve this problem, in our previous video we discussed about the kernel space and the user space, right, where the process runs in the user space, and if it wants to perform a privileged instruction, then it has to do a context switch from the user space to kernel space, and then the operating system will help it in making those restricted or privileged instructions. So please do go through the previous video about the user space and kernel space to understand this better. We have already discussed about this, how it works. Okay, and that solution is useful over here. Okay, that's one approach to do it. Okay, then the other option is switching between the processes, right? So how can that be achieved? If we want to switch between the running process and give the control back to the operating system, right, we wait for the system calls. A system call will basically invoke an interrupt handler. The interrupt handler will look for the particular interrupt service routine in the interrupt vector table, and we'll execute that particular function by the operating system, and then then the control will be returned back to the process. So we have discussed this as well. There is a video which I have already made last week on system calls and interrupt handlers. So that's one way to achieve switching between the processes, right? That's how we can also regain the control of the CPU. So please go through that video to understand this concept completely. But this is one approach to it. The other approach is, instead of waiting for the process to make a system call, the OS itself can take the control of the processor. One way to do is by using a timer interrupt. Okay, it is basically like an interrupt service routine only, but programmed to raise an interrupt every few milliseconds. Whenever the interrupt is raised, the currently running process will stop. Okay, a pre-configured interrupt handler in the OS will run. At this point, OS has regained the control of the CPU, and thus it can do whatever it pleases to do. It can probably stop that particular process and run a different one. Now let's say there is a process. In that process we write a bad code, we write a while loop which runs infinitely. Okay, and inside that while loop you're not making any system calls or anything. If there is no timer interrupt, then this process will run forever, right? Because it's a while loop, it's an infinite loop. But if there is an interrupt, timer interrupt handler, which will only run a particular process for a few milliseconds, and after that it will halt and it will give the control back to the operating system. Now operating system can decide what to do after that, whether it wants to run that particular process or it wants to run some other process. It will do a context switch and it will load the other process registers and it will run the new process. Okay, so this is one way to do it. The timer interrupt is easy. What happens is, when you, during the boot time and the OS is initialized, you initialize this uh, timer handler as well. You tell, what the timer handler has to do, and you start the timer. Okay, and once the process A runs and the timer interrupt happens, then in the operating system it will be switched from the user mode to kernel mode to handle that particular interrupt, timer interrupt, right? So then the OS will regain the control. Once OS regains the control, then you decide what you have to do based on your scheduling policy, where you are like, one particular process has ran for so many seconds and you want to run another process after it has reached a particular time interval. That could be your policy, or your policy could be simple, to just run another process once the interrupt has occurred. So based on your scheduling policy, you can switch the context. Okay, so this is how you're using a timer interrupt to achieve the regain of control from the process. Okay, so important things over here is the user space and the kernel space. There is a video already on it, please go through it to understand that concept, and the system calls and interrupt handlers, how that works. And then there is a timer interrupt, okay, which where you don't have to wait for the process to make the system call, but the operating system has the ability to regain the control over here. uh, Hope that made sense. Now let's quickly go through some of the system calls which we already have in the operating system. These are predefined system calls. The first one is the fork system call. The fork system call is used to create a process. Okay, let's see this example over here. In this example we can see that the this particular process is the main function running. In the main function, that means a process is running. So this is the parent process. Okay, hello PID 29146 219146 is the parent process ID. Okay, I'm doing a fork. That basically means I'm creating a child process inside this parent process. Now fork will can return three values over here. It can return less than 0, that means the creation of the new process has failed. It can return 0, that means the child process has been created and now you are in the child process context. Okay, so what happens is, at line number 7, either the parent process will continue executing or the child process will continue executing, and the child process will continue executing the same program from line number 8. It does not execute a new program. Okay, so if it's a child process, then it will go to the line number 12, that is else if condition, where RC is equal to 0, and it will print the child PID, which is 29147. If it is a parent process, then it will go to line number 15, that is the else condition, which returns the value of the child process ID. Okay, which is line number 17 will be printed, parent of the PID, which is 29147, that will be the return value, and the get PID will fetch the current process ID, which is the parent's process ID. Okay, now this is non-deterministic. Now we cannot guarantee that after fork whether the parent process will execute or the child process will execute. So it's possible that the line number 14 gets printed first and then line number 17, or line number 17 gets printed first and then line number 14. Now how to make it deterministic? There is another system called as wait. Okay, in this wait we generally use it when we are running the parent process. Okay, in the parent process line number 15, in that condition we'll use it. That means this parent process will wait until the child process has finished his execution, and only then the next instruction in the parent process will execute. So this is always deterministic. So even let's say after fork the parent process runs, it will come to line number 15 and it will see that it has to wait. then it will wait, then timer interrupt will happen, and then the child process will start running. Once the child process starts running, the line number 12 will get executed, line number 13 will get executed. Okay, and then once it returns from there, then we will run the line number 16 in the parent process context. So this is how the wait makes the fork the makes the execution deterministic, where we know that the child process will always run before the parent process. Okay, then the other system call is exec. Now we saw that once we do fork, it will always run the same program, but we do not want to run the same program, right? Once we create a child process, we want the child process to do something else. So this is where the exec function call is used. Okay, in the child process context, these are the arguments which I'm passing, which is wc is my first argument, and p3.c is an input argument to w.wc. wc is basically a word counting program, and I'm giving an input file of p3.c that is basically counting the number of words in that program. It's counting the number of bytes and number of lines, I think. Okay, and then I'll pass these arguments to exec function. Okay, and what happens is when you exec function never returns. Okay, it will never return, so line number 20 will never get printed. Once the timer interrupt occurs, the parent process will again start running. If the parent process has run first, then line number 22 gets executed, then the child process will get executed, then the control will come back to line number 23. Okay, so this is how we can run a different program in when we create a child process. Okay, now let's see over here. We did this. Hello PID 29383 is the parent process. Child process is this. Then 29384. Then it is executing the file wc with the word count, which is of the file p3.c. I think the number of it prints the number of words, the number of lines, and the number of bytes. Okay, and then the parent process gets executed. So this is actually useful in many cases, right? So let's say we have a prompt line, right? Unix prompt. It's basically any command you can run on the Unix prompt. Okay, like over here we have wc p3.c, and it's the redirected. The output is redirected into a new file.txt, right? So what happens is the Unix prompt is running as a parent process. It will create a child process with this particular command, and this particular command will be run as an exec. Okay, once it is returned, the parent process will again come back to the prompt, where it can take a new command and run a new command using the exec and the child process together. Okay, this way we can run multiple number of commands on the prompt. Okay, this is how the shell will run from the wait and prints out the prompt again, ready for the next command use. Similarly, we can use different types of commands in the prompt, like grep, like cat, and all of that, and there are like few more examples regarding that. Then there is an option to kill a particular process using the kill function. Okay, then there is sigint, which is sig interrupt. Whenever you give a control C, it will terminate the process. Then there is control Z, which is sig stop, which is basically pause the process in mid execution, and you can later give a command to resume it. Okay, so these are the different process calls. Okay, we can use to create a new process. We can use to create a new process to run a particular file using exec. We can kill a process, we can stop a process, we can wait for a particular process to complete. So all of these are used when we are doing multiprocessing. Okay, so multiprocessing programs will use all these function calls. So each operating system will have its own variant of these function calls. So just go through these examples. It will be very useful for you guys to understand how it works. Okay, so please do let me know in the comment sections if you have any questions. Please like, share, and subscribe. Thank you guys.